Hi, in this video I'm going to talk about the color basics because we need to understand the basics of color before we start doing complicated things like ICC profiling and color management. So let's talk about color first for a bit. First, how do we see color? Well, color is just a form of radiation of different wavelengths. So the wavelength of a radiation determines what kind of thing it is. It starts with gamma rays, goes up to X-rays, then ultraviolet light, visible light, infrared light, and radio waves. Just depending on the wavelength. So the longer the wavelength, the more it goes up. And the visible light is actually between a wavelength of 390 and 750 nanometers. So that's what we call the visible light. That's basically every light we can see. Now, how do we as humans perceive that color? Well, basically we need an eye, of course, to see color, and we need a brain. And then when a ray of light hits our eye, it goes through the iris, through the lens, and gets focused onto the retina. And the retina has rods and cones. Rods are responsible for the intensity of light. Cones are responsible for color of light. So different type of cones are sensitive to different basic colors, so the red, green, and blue. And that information from all of those rods and cones is fed to your brain through a nerve, a bunch of nerves. And then your brain, actually the green part in the back of your brain, interprets that information and makes you see color. So that's basically how it works. Now, your eyes, however, can deceive you. Try looking at this image and focus on the X on the image. So don't look at me, just focus on the image. And don't worry, I'm not trying to hypnotize you. I just want you to focus for about 15 to 20 seconds on the X before I will hit the next slide. And I want you to keep looking at the X as I hit it. And notice what happens when I do. You see color in the image. Now, until the moment you start moving your eyes around, you see color, the right colors that are in the image. Now, how does that happen? The image you were looking at was actually a negative. So it's just one with the colors set to negative. And your brain sort of hangs on to the color information it did get. It didn't interpret it very well because it didn't see it as natural color because it was a negative. But because it had that information, and then when I switch to the next slide, that information somehow got transformed in your brain to be color. Whereas if you look at the image now, there is no color. There's just a red X on a black and white grayscale image. So you're deceived by your eyes. Same thing happens here. It's not the same for everyone because it slightly depends on your eyes, but most people would not perceive the color red left and right to be the same. Now watch what happens if I move them close together. They are the same. Didn't trick them. They are exactly the same. It's even worse when we use a different color. I would swear that the color left is more magenta than the color on the right. And the color on the right is more towards the left square color. So the circles do not have the same color to me and to you, to anyone. And watch what happens if I bring them close together. They are the same. It's not a trick, it's just your mind and your eyes being tricked. Now, maybe you think that in grayscale, your eyes are much more neutral, much better. Well, they are. In a way they are, because your eyes are quite good, quite sensitive in noticing when a color is not neutrally gray. So when a color is not RGB, same levels, but one of the red, green, or blue channels is slightly higher or lower in a mid-tone gray, you can see that quite easily. Most people can see that. But you cannot see the difference if a color is, instead of RGB red 255, only 255 instead of, or 250 instead of 255. So 5 difference in red. When saturated, you won't see. 5 colors in red. When it's gray, you will. But still in gray, you are still fooled by your eyes. Because look at these rows of boxes. The top of the boxes alternate between a darker and a lighter color, right? I mean, everybody can see that. It's just a row of boxes with darker, lighter, darker, lighter. But watch what happens if I draw a gray bar across the image. Notice how the top of the dark box is exactly the same gray as the light one. They're all RGB 127. They're not different. I didn't change the image. You can still see the difference on the right side of the image, but if you move your eye to the left and then focus on the white arrows, you can see that they're all the same. Again, your eyes and your mind tricks you. It's not a reliable source of getting color information. Your eyes will deceive you. So, on top of that, 8% of the men are colorblind. Somehow, because of our chromosomes, men are more likely to have a color deficiency. So 8% of us cannot see the difference between red and green. That's the most common color deficiency. So that makes us very poor color assessors by default. So that is why we use equipment and software to manage colors in an accurate and consistent way. We need independent, consistent, neutral devices and software to make sure that color is consistent throughout a workflow. That's basically what we want to do. So let's look at color models. There are two fundamentally different color models out there that we use in a day-to-day basis. You have RGB, red, green, and blue, and CMYK. One is used for your camera and your display, the other is used for print. So the RGB is called additive, and the CMYK is called subtractive. That's quite logical because with RGB you start off with 0 black, and you add colors to get brighter colors up to white. And with paper you do exactly the same and the opposite of that. You have white paper and you subtract colors until you get black. So let's take a closer look at RGB and CMY, because those are sort of easy to calculate. So if you look at lower values of RGB, they give you darker colors, and higher values of CMY give you darker colors as well. So they're just, you can calculate easily what a CMY color would be from an RGB color. But the problem is that CMY makes together theoretically black, and on a screen it does look black, but on print adding cyan, magenta, and yellow ink will create something that's more like a muddy brown color. And the other problem is it's 300% of ink, because you need full magenta, cyan, and yellow to get to that color, which makes it hard to dry and hard to position, because they need to be exactly at the same spot to be accurate. And if you've all seen a bad newspaper print where the colors were offset a little bit and one of the colors just not in alignment with the rest of the colors, and then you see a color shift in the edges. So you don't want that, so that's why we added black in the printing process. So the RGB colors that we get just mix up to the different colors, so you can get yellow by adding red and green in an RGB additive model. Same thing happens in CMYK. If you add yellow and magenta, you get red as an ink on paper. The CMYK is used versus the RGB and not the CMY. And your RGB is of course used by your camera, your scanner, and your display. Different directions, but they're basically using RGB as a color model. And CMYK is used by a printer, combination with ink and paper, or a press with ink and paper. Those are not the same. So you have a lot of different CMYK variations, because once our paper changes, the behavior changes. The value of the CMYK value might give us a different color. And if we use a different camera or display, we get this different colors with the same value of RGB sent to it too. So that's a problem. We cannot get consistent colors because we have different RGB and different CMYK devices that give us different colors. So to solve that, we have a lab color model, which is a scientific color model. Don't worry, it won't get too complicated. Basically all it is a model in which you can describe and measure any color out there, be it RGB or CMYK. There is no color that is bigger outside the range of LAB. All colors are smaller than LAB. All colors can be described in an LAB value. And it's a three-dimensional color model. So where RGB is just 3 values, this is an axis model. So you have a luminance axis, which gives you light, the luminance. So dark luminance value means black, high luminance value means close to white. And you see the 4 layers I made on the screen just give you different luminance values of the A and B colors. And the A and B actually go from red and green and yellow and blue. So any color that's out there you can measure with a device that then translates that measurement into a LAB value. So that's how a profile is measured in an LAB color. So ICC color management, that's something that is the basis of all color management today. We're working with ICC profiles, and ICC stands for International Color Consortium. That's a bunch of guys that back in 1984 decided it might be smart to think of standards of how to get consistent colors through a workflow. Much has happened since 1984, but it's still under development. Color management is far from ideal and far from automatic, so there's still lots of complicated steps to take. But the basic principles behind it are good. Let me try explaining. So you have your 3 different type of devices: your cameras, your displays, and your printers or presses. And you have, of course, a computer, and you're gonna try to link them up and get them consistent by using an ICC profile. Now, how does that work? You have a color engine running on your application that's on your computer. That can be Photoshop, Lightroom, Aperture, any application that can do something with color information. So not your average Word on a PC, because that has no clue what color management is, but basically any application that can do anything with colors. So the color engine uses the information it gets from a file, because that file will have an embedded ICC profile. So the ICC profile is read from the camera file, and that is used by the color engine, and then the ICC profile for your display is used to translate that color from the RGB value through lab to the right RGB color for your display, or through the ICC profile for your printer to the right CMYK color on your printout. So the lab color is used as a scientific color model to link up the different ICC profiles, because basically all your profiles are tables from RGB to LAB or CMYK to LAB. So it's just a bunch of tables that say, if you send me this, I will get that. And if you send this color to the screen, I will actually display that. If you print this color to this printer, it will actually print out that. And the measurements is always done in LAB values. And that means that color can be managed that way. Because the color engine in a typical workflow would take the information in RGB, get to the right LAB value that corresponded with the measurement that was done with the profile, then look up that same LAB value in the display profile, and then translate that through the table to the right RGB value it needs to send to the display to get the same color that was intended by the camera. Or use the LAB value from the input profile to get to the output profile in the same lab color, and then read what kind of CMYK values are to be used to get the right printout. That is basically how color management works. Now, on this site you will see many videos going into the details of color management for either your display, your camera, or your printer. But these fundamental basic issues you need to grasp before you look at those, or it will just be learning tricks, and it's better to learn the basic fundamentals behind it so you can understand color a lot better, and it makes it easier to solve color issues as well. If you've had any comments on this video or any of the videos on the site, feel free to contact me, and I hope you find this useful, and I look forward to seeing you again.